Okay, welcome everyone. Hello to the last lecture of the day. I think I have the impression that this topic is not as well-established topic as the previous ones. So I'll start giving some context and motivation, and I hope it explains the name, which is quantum thermodynamics about. I don't know if it is a good name, but it's a name that is with which some community, I'm going to tell you about this, identifies. So as you know, the thermodynamics we study in the classical thermodynamics has a strong relation and impact with the industrial revolution that took place some time ago. And nowadays it is believed that is taking place a second quantum revolution. Actually, the first one started with the discovery and the development of the laser in photonics, and in solid-state physics with the discovery and the development of this transistor. So this is still in the museum of the old Bell Labs, now is Nokia technologies. So the transistor evolved from this old-shaped form, very big, to this very small and fast and efficient devices that we have in all our computers. And this is so basically the evolution of the first quantum revolution, and now it is believed that we are in experiencing this second quantum revolution, of which the paradigmatic device is this one, which is a quantum processor. As it was already said today, the logic of these two kinds of devices is quite different. The logic states of the classical processors are the bits, the 0 and 1s, as it was explained today, while the quantum processors rely on the use of this superposition of states, and they are implemented in the qubits. The big difference, so as we see in this evolution of the classical processors, there was a strong process of miniaturization. So the current processors now are of the very small size, micrometers, nanometers, and they continue reducing. So at the level of the size is more or less the same, the classical devices and the quantum devices, but the main difference is ones operate at room temperature, while these others operate at very low temperatures, and these are the conditions where quantum effects become important and relevant. So some experiments related to thermodynamics are the following. So I'm going to be biased. I'm not able to cover everything, but there are plenty of experiments on the study of thermoelectricity and transport, thermal and electrical transport, also thermoelectric transport in quantum dots. These are the typical device with which the quantum dots are fabricated. On the basis of these semiconductors, doped semiconductors. They made a sandwich, and they manipulate and work with techniques of nanolithography till they manage to, this is basically a big circuit, and this is the quantum dot. A few electrons are confined there, so this is a quantum dot, a sort of cut of the device, and a few electrons are confined there. This is another structure which is used to measure. So this is another quantum dot. I'm going to come back to this quantum dot at the end of the lecture. Fabricated with another material, but basically the main feature here is that you have a system containing a few levels, everything at a very low temperature, and in this case there is a small temperature bias. So it is investigated how the transport of the electrical transport and the thermal transport takes place under these conditions. Also, a small electrical bias is applied here, is indicated with this voltage V. This is another example of a quantum dot. So a quantum dot is a sort of a paradigmatic example of in which a paradigmatic device in which plenty of experiments and theoretical work is being done nowadays. And in this case, a small contact, so the quantum dot is implemented in this small contact. There is here a thermal bias as well as an electrical bias. And in this device, the strong correlations are important. So in this small region, the electrons confined there experience a strong Coulomb repulsion. And the Kondo effect takes place, and it plays a role in in this case, in the behavior of the thermoelectric response. Another very interesting playground is the quantum Hall effect. The quantum Hall effect, as you know, contains edge states which are topologically protected, and there are plenty of transport experiments in quantum Hall systems. I'm going to also mention this because later, because this is one of the verifications of the fact that the thermal conductance is the same for electrons and for other kind of particles obeying a completely different non-fermionic statistics. So this is also an experiment with quantum Hall edge states. In this case, the aim is to investigate how the heat is propagated along the edge states. These small islands here are also created with edge states and play the role of thermometers to measure locally the temperature in this small distance of the order of a few nanometers, and in this way analyze how heat is propagated along these edge states, which is basically a realization of a single or a few quantum channels for electrons, or in this case that we have a fractional quantum Hall effect, the fractionalized quasi-particles along these quantum channels. This is another example, in this case, with how heat preserves quantum coherence. These are two superconductors at different temperatures. Here we have a magnetic flux which induces a phase bias, and these are two Josephson junctions. And this experiment shows that the heat transported along this device keeps track on the phase, the phase generated by this superconducting, this magnetic flux there. So this is basically the phase bias, and this is the response the response to this temperature difference. So this is in superconductors, and there are also very interesting experiments in quantum circuits. In this case, we have these superconducting qubits, and this is a different kind of systems. Here we don't have electrons transported, so here is a sketch of the device. We have here a superconducting qubit coupled to resonators, and through the resonators to the rest of the circuit. These circuits have some resistive components, and through these resistive components it is possible to implement a thermal bias. And the heat transport through this combination of the qubit with the resonators keeps track of the coherence, of the quantum coherence, which is implemented and in the detection with this phase introduced here in the also with a magnetic flux in the superconducting qubit. Finally, there are also interesting experiments. In this case, are in metallic devices in these junctions, and in this case, it is detected the behavior of the quantum fluctuations, the quantum work fluctuations in these small devices by the thermal, the electrical response. At the level of cold atoms and cold ions, there are also experiments. This is a very interesting experiment of the implementation of an Otto cycle, Otto or Stirling cycle, some thermodynamic cycle in a trap. In the last lecture, I'm going to mention about this. In the case of cold atoms, there are also experiments on the thermoelectric response. So this is a system. So this is just a sketch, but this is a system of cold atoms, where some electrical bias and also some temperature bias is implemented, and it is detected the response of the particles under these conditions. So the main ingredients in all these experiments I showed is that they are small size and very low temperatures, as I said before. So these are the main conditions. And related to thermodynamics, there are all these open questions, at least. Maybe there are others, of course, but this is my selection. So there is a question about if these devices are energetically efficient or no, if they can be more efficient than the classical ones. At a more fundamental level, there is also the question about how energy is transported and dissipated, if it is possible to implement exchange of energy, to take advantage of the quantum conditions, to implement heat work conversion mechanisms. How are the fluctuations in these systems? Are they the same as in classical systems or no? And around all these questions and in good part motivated by all those experimental advances. There is a community, there are several communities, the main ones are listed there. People from statistical mechanics, cold atoms and ions, quantum information, quantum optics, condensed matter. So people from all these communities are looking at those phenomena, and this super community is identified as the community of quantum thermodynamics. Okay, so it's not a new field, but it's just looking at a phenomenon of the classical thermodynamics under a completely different context. So this is the plan of the lectures. Most of the lectures will be focused on the problem of heat work conversion. So about all the list, I'll focus on that problem. And today the idea is to focus on the case of steady state heat work conversion, and to relate, to focus in particular to the paradigmatic case of heat work conversion in steady state, which is thermoelectricity. It's a topic of quantum transport. I noticed that the lectures were originally announced as quantum transport, not as quantum thermodynamics in the school. So I think it's good. In the second lecture, I'm going to talk about finite time processes, the concepts of heat and work, how to define them in open quantum systems. Also on entropy generation and dissipation. I'll keep close to, you know that classical thermodynamics usually keeps close to equilibrium systems. Okay, it deals with purely equilibrium systems or situations which are close to equilibrium. If we go very far from equilibrium, we are going to study non-equilibrium physics, and it is more difficult to make contact with the thermodynamics. Then in the last part, the third lecture, I'll focus on cycles and in the problem of finite time heat work conversion. So this is the plan, so please interrupt me at any time. So let's start fast with the review of the laws of thermodynamics. This is the zeroth law. We know that if two systems are in equilibrium with a third system, they are also in equilibrium with each other. The first law tells us if we have a system that contains some internal energy, and if the internal energy changes, and the system, while it changes, is in contact with a reservoir, with a thermal bath, we can identify two kinds of changes of the internal energy. One change is identified as work. Work is are changes which are generated by control parameters. This is a sketch. Imagine that we have two control parameters that we call x1 and x2. If we change these parameters, we will change the internal energy of our system, and we identify those changes as work. Instead, if there are changes that are due to exchanges with the thermal bath, those changes are identified as heat, and the first law tells us that the total energy is conserved. The second law, this can be stated in different ways. We are going to use this one due to Clausius, and tells us that if the system evolves between two states that we call A and B, does some evolution while in contact with several bases, which in principle may have different temperature. The change of the entropy defined in this way, so we have to add all the heat exchanges. Sorry, here should read J instead of 1. All the heat exchanges divided by the temperatures with each of the bases. This quantity should be always positive, and finally, the third law tells us that as we approach zero temperature, the changes of the entropy tend to be 0. I'm going to focus with the so-called fourth law. But to arrive at the fourth law, I need to provide some context. And the fourth law is interesting because it's the first approach to away from equilibrium. Focuses precisely on the problem, makes connection to the responses towards out of equilibrium, and it's very important to understand the problem of heat work conversion. So let's assume that we have a system which has a well-defined particle density and energy density as a function of the position and as a function of time, but it is not uniform, so there is no constant particle density, non-constant energy density. There are fluctuations as a function of the space and time. But let's define that these changes are not very large, that they are small, and that we can define locally temperatures and chemical potentials. Then let's define the entropy. So the entropy, or the change in the entropy, sorry. We are interested in the changes of the entropy and actually the entropy density. We are talking about densities here. And as we know, the entropy is a function of the extensive parameters, so we can express this change as a function of time of the entropy in this way. The change of the entropy with respect to the extensive parameters times the change of the extensive parameters with respect to time. And then we identify things. We identify these changes of the extensive parameters. So the extensive are the energy, the number of particles, and the volume, for instance. And these changes of the extensive parameters define the fluxes. And the changes of the entropy with respect of the extensive parameters define the so-called affinities. So this will be related to the changes in the chemical potential, the temperature, and so on. In general, all these fluxes are functions of the extensive parameters. In principle, they are functions of all the of all the affinities, and they may be very complicated functions. But we know that at leading order, we can expand these fluxes linearly. Maybe we don't have this leading order, the linear terms vanish, but in principle it's a good assumption to say that these fluxes are at leading order linear functions of these affinities. So we have these coefficients that appear here that receive the name of Onsager coefficients. These are the coefficients that describe the response of the fluxes as a function of the affinities, changes in the chemical potential, changes in the temperature. And it is important that this is the linear term. All these quantities that are response functions are functions which are evaluated in equilibrium. Otherwise, we won't have a linear order. So they are evaluated exactly when these affinities are equal to 0. And because of that, they obey the micro-reversibility. So this is, sorry, before going to that, this is just substituting in the first, in the definition of the rate of change of the entropy, substituting the linear dependence of the fluxes with the affinities. This is important to have in mind that this rate of change of the entropy, so this is basically the entropy production, is a bilinear function of the affinities, and what appear here are these Onsager coefficients. And then it comes the fourth law. The so-called fourth law, or also named Onsager theorem, which tells us that these coefficients are not independent. They are related by these Onsager relations. So this is a sort of third law in mechanics that tells us that if there is a force, there is also a reaction, like the action and reaction principle. This is a sort of that law at the level of thermodynamics. In the presence of some magnetic field which breaks time reversal symmetry, we may have a plus or a minus here, and this depends on the type of response functions that we are dealing with. In particular, it depends on so these response functions are related to susceptibilities, typically involving the dynamics of two operators at different times. These are correlation functions. And depending on the parity of these operators entering in the response functions, we may have, under some time reversal inversion, we may have a minus here instead of a plus, but these are related. So now let's go to thermoelectricity, which is a context where this fourth law and Onsager theorem plays an important role. Also, yeah, the second law, everything. Okay, what is thermoelectricity? This is a definition given in Wikipedia. Thermoelectricity is the possibility of converting a temperature difference into an electrical voltage, or vice versa. And it's basically some device, some conductor, in which we can apply a temperature difference and also an electrical voltage. We have a response, an electrical and a thermal response. And we can make this conductor connected to these two reservoirs work as a refrigerator. In this case, we apply some current and we get some effective heat flowing from the cold reservoir to the hot reservoir. And we have also this other reverse operation in which, as a response to a temperature difference, we can generate some electrical current. So this is thermoelectricity. At the level of our quantum conductors, we have here our quantum conductors connected to two reservoirs at which we apply a difference in the chemical potential and a difference of temperature. We will have in mind that eventually we will have expressions for in terms of Hamiltonians for all these systems. So we will have some Hamiltonian for the left reservoir, some Hamiltonian for the right reservoir, some Hamiltonian for the conductor, and also for the contacts between all these systems. And in this case, we will have two affinities. The affinities will be defined by the difference of this chemical potential and also by the difference of temperature, and two relevant fluxes, which are the heat flux and the charge flux as a response to these affinities. So these are the definitions of the fluxes in this context at the level of a quantum system described by Hamiltonians. The natural way to define the energy flux entering one of the reservoir with this alpha, maybe the left reservoir or the right reservoir, will be the rate of change of the energy stored in that reservoir. And the same applies for the particle. And if we have electrons, it is not, we cannot simply identify an energy flux with a heat flux. So the heat flux is defined with this relation. And this can be seen if we go back to our definition, our original definition of the rate of change of the entropy. We will see that the response to the temperature difference will be not only the energy flux, but also this combination this energy flux minus the chemical potential times the particle flux. So the way in which we can theoretically compute all these fluxes is computing precisely the rate of change of the energy stored in the reservoirs. And I'm going to mention in a while, briefly, two different ways to compute this. So this is a non-trivial problem in general. We need a good method. So at the level of the thermoelectric description, the thermodynamics description, we, as I said, we can identify the two affinities and the two fluxes, and this is how the linear response looks. So we have the electrical current, which is some coefficient that will be related to the electrical conductance times the electrical affinity. This is the difference in the chemical potential. Here enters the electrical voltage, plus some coefficient that is the response to the thermal to the temperature bias. So we have an electrical current, a component of the electrical current, which is a function of the response to a temperature difference. And this is what happens for the heat current, the heat flux. The heat flux will have some coefficient, will be given by some coefficient, which is clearly related to the thermal conductance, which relates directly the thermal current to the temperature difference. But we also have this other coefficient, which tells us that we can generate a thermal current as a response to an electrical voltage. So these ones are trivial. These diagonal ones are more or less trivial. These ones are non-trivial. This one is named the Seebeck coefficient. The other is the Peltier coefficient. These are related by Onsager relations. Yes? Sorry?
Which extensive parameter is true
So the two extensive parameters are the particle current, the particle number, and the energy. And the energy, yes. And yeah, so coming back, so the diagonal ones are the trivial responses, while these other ones are the non-trivial, the off-diagonal, and these are the responsible to the heat work conversion. So you see, in order to have this, all these mechanisms of the machines I mentioned before, we need, for instance, we have some temperature difference. The trivial response is to have a heat current. But if we want to have a refrigerator applying a voltage, we need to put this other response into the game, yeah? So this will be the responsible to compensate the usual thermal current, the usual thermal flux as a response of the temperature difference. Otherwise, the heat flux will always flow from the hot reservoir to the cold reservoir. We want to get some net flux from the cold to the hot. So we need this one to have, furthermore, we need this one to have a sign which is opposite to this trivial contribution in order to have this effect of cooling. And something similar takes place here with the Seebeck response. So these green parameters are the contain precisely the information of the heat work conversion. So these are the definitions. As I said, the L11 coefficient is related to the electrical conductance. We have 1 over T here. The thermal conductivity, the thermal conductance is related to the other one, or when there is also a contribution of the off-diagonal ones, it is defined in this way. And the Seebeck and the Seebeck and the Peltier coefficients are related to this L12, and which is equal to the L21 by Onsager relations. Yeah, so this is a summary. The Onsager relations mean that these two are the same. In this case, they are the same. We don't have this minus here. This is the rate of entropy production. This is the heat flux entering the left reservoir divided by the temperature of the left reservoir, the same for the contribution of the right reservoir. And as I mentioned before, this rate of entropy production in linear response can be expressed as this bilinear combination of the coefficients with the Onsager matrix here. In order to be in agreement with the second law, we need, besides the Onsager relations, we need some other conditions that these coefficients should satisfy. These are the fact that the diagonal ones should be positive, and also the determinant of this Onsager matrix should be positive. These two conditions will lead us to a positive rate of entropy production. Okay, so we have two operational modes, as I said. There are these two operational modes are the heat engine, in which we can, given electrical power, we can, given heat, we can get as a result electrical power. So if we define the efficiency in this case, it will be the electrical power that, in terms of the flux and the affinity, reads like this. We have to, as this x1 has some 1 over t, is defined as 1 over t, we have to put some t to compensate. And as the delta mu is EV, we have to put some E to compensate. What we have to invest here is heat, and this is precisely the coefficient J2. We can show, it is quite a simple calculation, that if this, I didn't include that, but this is a calculation that can be done. If the second law is satisfied, so if the coefficients satisfy these constraints, then this quantity should be less than the Carnot efficiency. While in the case of the refrigerator, okay, so I used here the letter eta for the case of the refrigerator or heat pump. It is usually used the coefficient of performance instead of the name eta. But anyway, so in that case, what we have is, as a result, the heat extracted from the cold reservoir, and we have to invest electrical power. So it's basically the opposite of the result for the heat engine. And we can also show that this is bounded by the Carnot coefficient of performance for a Carnot machine operating as a refrigerator. Okay, it is usual to parameterize this, or first of all, to ask the question about which is the maximum value that these quantities may achieve given a value of the temperature difference. So given some delta T, how we maximize this function with respect to the voltage, and the result is the following. We have some, in both cases, we have that the maximum value that can achieve this efficiency or coefficient of performance is the Carnot efficiency times this factor. And this factor depends on this quantity that receives the name of ZT. ZT is the so-called figure of merit of the machine, and is the following combination of the Onsager coefficient. So this is actually, these two are the same because of Onsager relation. So it's basically L12 squared divided by the determinant. And you see that the higher this ZT is, the closer to Carnot efficient the machine is. If this goes to infinity, this eta tends to the Carnot ideal Carnot efficiency. I would like to mention this review wrote by these colleagues, which is very good, very didactic, if you want to read more about thermoelectricity in general, and in particular in the quantum regime. I think this is a good place with plenty of references. And they start precisely arguing with these arguments about the definition of the figure of merit ZT. And they compared, they put numbers, they do this easy calculation, and you see, in order to be more or less machine competitive, we would need to have 1/3 of the Carnot efficiency, and this, in terms of this ZT, is a number of 3, more or less. And why is thermoelectricity not so much used at the room temperature or in general? It is because it is very inefficient. It's a very inefficient way of heat work conversion. So this is all the other mechanisms in the nature to implement heat work conversion. As you see, thermoelectricity is here, one of the lowest. But you see here that this is plotted mainly for high temperatures. In spite of this fact, there is a big activity to investigate new materials in order to improve this number. And this is a recent article, and there are some numbers here. Here there are no indications of the temperature, but most of these results are for high temperature. These are macroscopic materials working at a high temperature, and it is interesting because we could use domestically this mechanism as for generating electricity out of heat, and that would be fantastic. So this is one of the interesting applications of thermoelectricity. It is used in these spatial missions because here this is a thermoelectric generator, which is, so there is some nuclear reaction. It has some radioisotope, which generates heat, and with this electricity is produced. This is very stable in spite of the fact that it's not efficient. So what happens with thermoelectricity in the quantum regime? So in this regime where we are working in small sizes and at very low temperatures. So these are very special conditions because phonons don't play a very important role. Phonons are always there, but in this at very low temperatures, they are quite not important. Under these conditions that the device is very small and we have very few quantum channels, we are also in the conditions where electrons propagate coherently along the conductor. So basically the situation, so this is what happened at the macroscopic scale, and this is our situation of interest in quantum systems. So we have a very small size system here where the electrons preserve the coherence when they propagate. We have here a few quantum channels, and this is the scale of thermalization. Deep in the reservoirs, we have macroscopic reservoirs, so all these cables, all these contacts at the end are macroscopic reservoirs, but we have here our quantum system. So this is the topic of interest in the quantum, the context of quantum thermodynamics. And it turns out that the special situation, as phonons don't, assuming that phonons don't play a role, we can fully characterize the two fluxes in terms of, so this is the electrical flux, the thermal flux. We can characterize both of them in terms of a single transmission function. These are the difference of the two Fermi functions describing the properties of the temperatures and the chemical potentials of the two reservoirs. And this transmission function contains all the information about the microscopic properties of the quantum system connected to the reservoirs. So here is some a summary of the properties of this transmission function. It behaves as a transmission probability. It describes the transparency of the quantum conductor. I'm always talking in this lecture about this two-terminal configuration, not several terminals, only one cold reservoir and one hot reservoir. So it depends not only on the properties of the conductor, but also, in principle, on the contacts how good are the contacts, and so on. Defines a probability. Basically, this is the definition. This is the probability of injecting an electron from one of the reservoirs with a given energy E and transmitting it through the conductor, and afterwards injecting it into the other reservoir. For a single conducting channel, and in the case of a perfect transmission, this coefficient is exactly equal to 1. And in general, it is a positively defined function. It behaves as a probability of transmitting the electrons. How to calculate this transmission function? Of course, we need the Hamiltonian for the system, for the contacts, for everything. There are several ways to calculate it, but there are one which is especially easy and that applies to many cases in which there are no many-body interactions. When there are no Coulomb interactions playing a role, for instance. This is a good, famous, and very much used way to calculate the transmission function. So think about the first lectures of quantum mechanics, in which we have some barrier, or we can have, so a quantum, remember the quantum dot I mentioned is a system with, which contains a few levels, and we can get a system with a few levels if instead of having one barrier, we have two barriers, and we will have some few levels there. And imagine that this is we can inject particles with the given wave function from the left reservoir, the left hand side. These particles will have some probability of being transmitted and being reflected. We can formulate also the problem from the right hand side. And in general, if we know the Hamiltonian, we can solve the Schrödinger equation for this part. For this part, we can put matching conditions for our wave functions. And in this way, we can write expressions like this, that the amplitudes of the wave function at the left are related with the ones at the right, and the matrix relating both is the so-called transfer matrix, the M matrix. From there, we can get the scattering matrix. The scattering matrix relates the outgoing amplitudes with the incoming amplitudes. In our case, the outgoing are the F and the B, the incoming one are the G and the A, and we have this scattering matrix relating both amplitudes. In this scattering matrix, so appears the transmission. So the transmission is precisely the coefficient relating what enters with what goes out of the conductors. And from there, doing this calculation, we can extract the transmission function. The complementary coefficient is the reflection, which is 1 minus the transmission. It is this one. So this is a very easy way. In some cases, like, and very practical if we have models formulated in the continuum, in terms of continuum Hamiltonians with something here in the middle. In other cases, and this is sometimes usual in the case of the quantum dot, we have this other type of Hamiltonians. We have for the quantum dot, this is for the case of an ideal and very simple quantum dot with a single level with the two possible spin orientations. We can accommodate here up to 2 electrons with the two different spins. And this for the reservoirs, we have basically free electrons, like electron gases with a given dispersion relation, and we have this kind of tunneling-like expressions for the contacts. So the electrons can jump from the reservoirs, left and right reservoirs, to the electrons. So for this way of formulating the problem, it is more appropriate in these problems in which we have these discrete Hamiltonians, is more appropriate to work with non-equilibrium Green's functions. I would need several lectures to explain the method, but it's a very powerful method that can be extended also for the cases in which you have many body interactions here. Okay, so this is just to give an expression for this case of the quantum dot. This is how the transmission function, the calculated transmission function with this method of the Green's function looks. We have here the so-called retarded Green's function. This retarded Green's function describes, so this is the expression. You see in the expression we have that this is a retarded Green function, and the fact that this retarded appears in the fact that we have an imaginary part which is always positive. And the imaginary part contains precisely the information of the contacts to the reservoirs, and contains here the information of the imagine that this contacts to the reservoirs is very small. So these terms are very small. We will have here a pole, and we will have basically this will tend to a delta function at the energy of the energy of the levels of the quantum dot. And in general, this is a function which is a sort of with the imaginary part of this function is some Lorentzian function or something which contains the fact that we have the quantum dot defined by several levels, which are widened by the contacts to the reservoirs. Okay, if we calculate this can be done quite easily in this problem, and we get this expression for the transmission function. Look, I'm here putting this sigma to indicate that we have the two spin orientations, so we have effectively two quantum channels here. And as you see, for this transmission function has the form of a Lorentzian. Keep that in mind because it's important. How am I doing with time? Okay, so yeah. Just a comment, the formalism of Green's function and the Landauer-Büttiker formalism, the one of the formulated in terms of the scattering matrix, are exactly equivalent for the case of systems described by bilinear Hamiltonians. If we have a system with many body interactions, Landauer-Beauty curve doesn't apply, but we can still work doing approximations with the Green's functions. A comment before going on is the fact that for the case of bosonic systems, we can also apply both formalisms, and we can, in the case of bosonic systems, imagine that we have a line of phonons, for instance. In that case, the only possibility, the only flux, the only possible flux will be the heat flux, which in that case is exactly equivalent to the energy flux. And if we work with any of the two formalisms, we will end with some expression for the heat flux, which has a very similar form as the one I derived for electrons, except for two facts. One fact is that we don't have here the mu, the chemical potential, and except for the fact that we, instead of having the Fermi functions, we have the Bose-Einstein distribution functions in this case. At this point, I propose you as an exercise the following exercise. Take the two expressions for the heat fluxes, the one for electrons, the one for bosons, for bosonic excitations. Assume that you have a perfect transmission, so that the transmission is equal to 1 in both cases, and calculate the thermal conductance. In both cases, you will have exactly this quantity. And this is an interesting result which was previously predicted with the different reasoning by Pendry and by Bekenstein. So this is known as the thermal conductance quantum. It's a quantity that is linear in the temperature and depends on a fundamental from fundamental constant. And the experiment I showed at the beginning in the quantum Hall effect was one of the experimental verifications that this result is valid. There are other in bosonic systems, and this is something very interesting, the fact that the heat quantum doesn't depend on the statistics of the particles involved. So let's come back to thermoelectricity. So far, I made a sort of intermezzo to comment briefly possibilities to calculate this transmission function, but we were at this point that in a quantum conductor we can calculate the heat and the electrical fluxes from these expressions. So the way to get Onsager coefficients here is basically just to expand this Fermi, so the temperature and the chemical potential enters only in the Fermi function, so we can expand for small chemical potential differences and for small temperature differences. And yeah, this is a quite simple expansion. We stop at linear order, we substitute in those expressions, and we get the following expressions for the Onsager coefficients. So this is for the case of the electrical conductance. These are for the off-diagonal coefficients, and this is for the one related to the thermal conductance. this quantity I here is an integral that appears here, and it's the argument contains some power. This power is the one indicated in the end here. The transmission function and the derivative of the Fermi function. And we see here that the possibility of having thermoelectricity in this context fully depends on the properties of this transmission function. Okay, so this is just a comment that, no, it's okay. So from given the Onsager coefficients, we can go and calculate explicitly the conductance, the thermal conductance, and this is the ratio between them. The ideal an ideal conductor corresponds, a perfect conductor corresponds to one which has the thermal, the transmission function equal to 1, and this will give us the bound for the electrical conductance and for the thermal conductance. And we see that this bound for a perfect conductor is in agreement with the Biedermann-Franz law. Do you remember the Biedermann-Franz law that we learned for ideal metals? Okay, in this case, if we have a perfect conductor, we recover that Biedermann-Franz law derived in the textbooks for ideal metals and so on. Okay. So, but what about the thermoelectric response? So I said, so it depends, of course, on the properties of this transmission function. So let's look more closely at these off-diagonal coefficients. The off-diagonal coefficients read like this. We have this function which is odd in epsilon minus mu. We have this function, the derivative of the Fermi function, which is even. So it's clear that in order to have a non-vanishing result for this coefficient, we need some function here which is not even in epsilon, in the energy relative to the chemical potential. And from intuitively, this can be seen as follows. Imagine that you have a perfect conductor. So a perfect conductor is the one which has a transmission function equal to 1. Imagine that it is connected to these two reservoirs at these two different temperatures. So this is the hot reservoir, so you have plenty of particles promoted from below the Fermi sea to these excited states, and this is the cold conductor, you have just a few. And what happens as a response, which is the electrical response to this thermal, to this temperature difference? Okay, these particles will have empty states here, so they will flow in this direction. But if the transmission is the same for everybody and for all the energies, all these electrons will also try to flow to this empty states here. So a perfect conductor which has a flat and always equal to 1 transmission function doesn't have thermoelectricity. In order to have thermoelectricity, we have to implement some conductor which behaves as an energy filter that prevents some of these processes that generate some asymmetry and favors one of them. So this is another way, intuitive way of what I said before. We need some structure function here because we have here the product of an even function with an odd function, and if we compute this integral, we will have a 0. We need something which has some convenient dependence on the energy. And this is precisely what quantum dots do. As I said before, the quantum dots are well described by this type of transmission functions, which have the form of a Lorentzian. And you can compare these two plots. This is for this transmission function, the Lorentzian function, and this is the plot for the derivative of the Fermi function. And you see that if you fix this, this Lorentzian is centered at the energy of the quantum dot. If these two peaks are put one on top of the other, we will have both functions which are even, and we will be in this situation. We will have the product of these two functions will be even. We have to multiply by an odd function. We won't have thermoelectricity. It's like putting this energy filter here, which is with respect to the Fermi energy exactly symmetrically. We won't do what we want to do in order to have thermoelectricity. But if we put this maximum of the transmission function at some energy, I would need some movie, sorry. If we put this maximum of the transmission function at some of, sorry, this is the transmission function, this maximum of the transmission function at some point here, for instance, we will have in a situation where within the relevant transport window, which is defined by this width of this function, will behave as an odd, effectively as an odd function, and we will get some thermoelectric response. So this is precisely what, because these quantum dots are very good for thermoelectricity, as I showed in the introductory slides. And the other point to comment is the fact that this is useful for experiments, that if we are at very low temperatures, this derivative of the Fermi function tends to the delta function. So, and this is the definition of the conductance. So we can infer the behavior of the transmission function from the behavior of the conductance. So this mu, this mean chemical potential, can be manipulated in experiments by different means. And this is a way to get some intuition on the behavior of the transmission function of the system under investigation, given the behavior of the conductance. And yeah, so I'm coming back to this is the first slide I showed in some more detail. We have here the quantum dot in the middle of these reservoirs with a temperature difference and also with the bias voltage. These are details of the device. This is the behavior of the conductance. So in the quantum dot, what they can do is to manipulate the level of the quantum dot, the energy of the level of the quantum dot, with the so-called gate voltage. This is what is plotted here. So you see that this conductance has some peaks, and these peaks indicate that, so this the same peak, sorry, at the different temperatures, and these peaks precisely indicate that we have the level of the quantum dot here. So this is delta is measured with respect to the energy of the level of the quantum dot. And we see that exactly at the energy of the level of the quantum dot, there is no, so this current is the current measured as a response of the temperature difference. So this TH means thermal. And we see that for this case, we don't have any response, but as we move a bit away from this situation, we can have this type of response that indicates that we have thermoelectricity there. So this is a device that has thermoelectricity. Okay, so a last comment. So I'm almost finishing. All I mentioned so far was basically in the absence of many-body interactions, but many-body interactions in this picture can play an interesting role. And these are some works, so it was not serious, so this is not a serious compilation, but this is just to give you some idea. There are much more works on thermoelectricity on non-interacting systems than on interacting systems, but I think the role of interactions is an interesting topic. As you see, that there are some of them even in systems which don't have electrons. So these are studies, recent studies of the thermoelectric response. Okay, so which is the main take-home message of these lectures? Is that in order to have a thermal machine, in our case we focused on the case of steady state and in the context of thermoelectricity, the most important thing is the existence of some mechanism for heat work conversion. In the case of thermoelectricity, it's completely clear. Not any conductor is a thermoelectric conductor. Not any conductor will give you a machine, a thermal machine or a refrigerator. In the case of thermoelectricity, this mechanism of heat work conversion relies on the existence of this energy filter, these special properties of the transmission function that implements some mechanism for particle hole symmetry breaking. And the other take-home message is that heat work conversion always comes with some generation. Recall that we started from the definition of the entropy production. So given all these things are not separated, they come together. Okay, thank you very much.